the invitation. This is my first visit to UK, so I'm very happy to be here. This is a joint work with Professor Okamoto, and for a long time we have studied bifurcation problem of water waves, and in 2001 this book was published, and afterwards we made some new additional results and some pending problems still remain. But among them, recently we made some progress in computation, numerical computations, so today's talk is about it. I will consider water waves consisting of two layers with a piecewise constant vorticity. Regarding the work, the papers of Professors Konstantin, Martin, and Matiuk gave us good suggestions, so we consider sorry. So theoretically, most part of the work is based on their mathematical framework. So the problem is a bifurcation problem of complicated structure of solutions with many parameters. So it's very quite difficult to classify them mathematically. So in order to see them all, we resort to numerical method with systematic computations. So it's my pleasure to show our numerical result in front of them. But before that, I will recall our past work that motivated the work. So the problem discussed here is to look for progressive water waves which move to the right at the speed c, and we consider these assumptions, usual assumptions. Gravity, surface tension are considered, and the wave profile is periodic and symmetric with respect to the y-axis. And we consider the rotational case and irrotational case. If we take a coordinate system xy moving together with the wave, then we may consider the problem in one periodic region. And in the moving frame, the wave profile is stationary, and there are underlying flow which move to the left at speed minus c. Depth of fluid may be infinite or finite, but for the present we consider the case of infinite. The basic problem are described in this way. Unknown functions are the stream function psi and wave profile hx, and the function f psi is the given vorticity function. So in the case of rotational, f equals 0. And Bernoulli conditions, and this is implies from periodicity, and the last one means the flow is uniform at infinity. And these constants, g is the gravitational acceleration and t is the surface tension coefficient. These two are to be of bifurcation parameters. The problem has been the subject of very many researches, and even the restricted problem has been turned out rich to be studied. To study the problem, mathematical and numerical difficulty is that the free boundary Hx is not known in advance. So in order to overcome it, we used the following method. In the case of rotational flow, we used these two methods. In both methods, using a velocity potential and a stream function, it can be transformed to a fixed domain, and formulation based on Levi-Civita. We put f equals phi plus I psi. Here, phi is a velocity potential and psi is a stream function. And we introduce the independent variable zeta and dependent variable omega like this. Then zeta run a unit disk and omega is an analytic function. So based on Levi-Civita, it can be formulated in this way. Find a function, find an analytic function omega that satisfies this equation on the boundary. These are examples of rotational flow of mode 1-2. For more information, please read our book. And on the other hand, in the case of rotational flow, another difficulty arises, because we cannot use the velocity potential. So instead, we used the following methods, but both of them have a merit and a demerit. When f is a general function, according to Seidler, it can be transformed to a fixed domain using a pseudo potential. This method is applicable to general f, but it is a demerit that we have to solve in the full domain. And when f is a constant and single layer, it can be reduced to the boundary integral equation according to Schimen and Safman. The issue for stagnation points is important. If there is one layer of constant vorticity, namely f psi is a constant zeta, then the stream function psi is assumed to be of this form, and here large psi is the rotational part. Then according to Schimen and Safman, it can be analyzed by an analytic function, and after using Cauchy integral formula, we have boundary integral equation of gamma t. Here, unknown function gamma t is parameterization of free boundary. These are the examples of gravitational rotational waves of infinite depths and with positive zeta. A stagnation point appears. Then how about negative zeta? As shown here, when zeta is negative, stagnation points do not appear. These are the case of gravity waves. Then how about capillary-gravity waves? This is our result in 2004. In the case of capillary-gravity waves, we couldn't find stagnation points. And summarize this part. Our task is to see whether capillary-gravity rotational waves have no stagnation point, and how to study a role of vorticity. And it is essential to use a method to include a stagnation point. Based on this issue, I will move to today's main topic. In these papers, the authors considered theoretically, water flows consisting of two layers with piecewise constant vorticity. And based on them, we made numerical computations in the case of two layers. And our purpose is to see when and where stagnation points appear. Then, why two layers? Vorticity is created near the bottom by the friction or near the free surface by the wind. Therefore, two layers vorticity is a step closer to real water wave. As for numerical difficulty, if in the case of single layer, it can be reduced to the computation of harmonic function via this form and eventually to the boundary integral equation. But in the case of two layers, no such reduction, and computation becomes substantially more difficult. We consider the basic problem with finite depth, so the boundary condition at the bottom it is replaced by this equation. Here, P0 is a constant determined by the flux of the flow, and in the Bernoulli condition, we put the coefficient of surface tension term as sigma, and the constants in the right side as Q. We consider the flow consisting of two layers different constants for vorticities gamma 1 and gamma 2 in omega 1 and omega 2 respectively, and we put the interface between omega 1 and omega 2 as y equal fx. In order to overcome the difficulty of free boundary, we used the following transformation, namely, we put q equal x and p equal minus psi, then the free boundary problem is transformed into a fixed rectangular domain. Here, the function h bar is the contour of p equal minus psi, namely the height function to be determined. We put h bar equals small u and large u in omega 1 and omega 2 respectively. Then we have the height function formulation in this way. The vorticity equations for small u and large u, and Bernoulli equations, and the boundary conditions for small u and large u. P equal P1 corresponds to the interface of omega 1 and omega 2, and this is a condition that the velocity is constant across the interface. Due to symmetry, we consider the problem in the right half in this way. We start from trivial solution, whose streamline horizontal, and the mean depths of omega 1 and omega 2 d1, d2, and they are related to p0, p1 by these relations. Then there is a trivial solution like this, where q and lambda are related to each other in this way. And as for bifurcation solutions, there exists a bifurcation point of mode n when lambda sigma satisfies the following equation. For a different gamma 1, gamma 2, when this relation is satisfied, then there exists a bifurcation point of mode n. And if positive lambda is given, then sigma is determined uniquely by this equation, So in our computations, let lambda be fixed and sigma be an unknown to be solved. This is an example of result by the height functions formulation. Start from a trivial solution, and we successively apply the Newton method and arrived at these solutions. But we couldn't compute further in either of these cases. The reason is that a stagnation point emerged here. So to see that, we delivered these data to the following new formulation to include stagnation points. This method is based on this paper. Received data, the above data of f and h, then transform omega 1, omega 2 to a fixed rectangular domain by these transformations. The free boundary, the interface, and the bottom corresponds these flat lines. And the governing equations are obtained as follows. We put psi equals psi 1 and psi 2, then governing equations transformed these equations in frame, Bernoulli equation, the boundary operator, and the elliptic operators. Outline of numerical method. In the first program, we solved the height functions and for several steps from a trivial solution, and we put the boundary and the interface f and h and deliver these data to the next program. In the second program, unknown functions f and h and assumed function psi 1 and psi 2 in full domain. Regarding approximations, we use Fourier series expansion approximation for f and h and finite difference approximation for psi 1 and psi 2. We iterate the following steps while changing b1 a little by little. That is, we use Konstantin-Strauss framework for water waves without stagnation points, and if the numerical computation does not proceed, we switch to the new formulation which allows stagnation points. Now then, turn to our experimental result. These are the parameters that can change the value. Mean depth D1, D2, we examined these 5 cases. And gamma 1, gamma 2, these 6 cases, namely combinations of the 2 from 0 positive value and negative value. And these 2 values about lambda. We experiments with combinations of these values of parameters. At the beginning, 2 examples as an introduction. Regardless the value of these parameters, please attention to bifurcation diagram and streamlines. In the left diagram, the horizontal axis represents sigma and the vertical axis represents norm of h. And the right diagram is a view from sigma direction. And green curves represents mode 1 branch, and red one represents mode 2 branch. And streamlines of solutions at the point A, B, C is like this. And trivial solutions are here. And there is a bifurcation point of mode 1 here, and the branch extends like this, and finally join mode 2 branch. And mode 2 branch emanates from trivial solution and join a trivial solution again. One more example. In this case, a stagnation point appears. And stagnation point, streamline of solutions at the point from A to E, and stagnation point appears like this, but will disappear like this. And in this case, this navy blue shows the part of solutions where a stagnation points appear. And in this case, mode 1 branch does not join mode 2 branch. Now I will show in a little more detail. First, to see when and where stagnation points appear, it is summarized in a table. And the first one is for smaller lambda. In this figure, the vertical rows are of the same D1 and D2, point 1 to 1 and point 1 to point 5. And the horizontal rows are of the same sign of gamma 1 and gamma 2. And streamlines are plots of the highest wave of each solution, so they are drawn at different scales. And we can see stagnation point. And a stagnation point appears in these 7 places. Then how about for larger lambda? In this case, stagnation points appears 14 places, and 2 places with blue flame, stagnation points appears for a moment and will disappear soon. Namely, we can find much more stagnation point than smaller lambda. And this figure shows various places where stagnation points appear. The first 2, it appears in omega 2 where gamma 2 is negative, and the second 2, it appears in omega 2 and where gamma 2 is positive. And the third 2, it appears in omega 1 where gamma 1 is positive. From these figures, we cannot decide which side of positive lambda or negative lambda. And in these figures, the ratio of D1 and D2 seems not to affect the appearance of stagnation point, but however, please see the bottom. These are of the same gamma 1, gamma 2. And in the right 3, stagnation point appears in omega 1, but in the left it appears omega 2. It changes somewhere between these two. So we have to study in more detail about this point. Next, I'll shift to bifurcation structures. Let me remind you, two kinds of bifurcation diagram were introduced at the beginning, and I will show you a bit more detail. In this figure, D1, D2, gamma 1 are fixed. Only gamma 2 changes like this, 0.7, 1, 1.11. And as gamma 2 becomes larger, then the loop becomes smaller, and larger than this value, we couldn't compute solutions. And in the right two, the mode 1 branch joins mode 2 branch, but in this figure, it doesn't join mode 2 as shown in the next slide. This is the enlargement. Mode 1 branch emanates from a trivial solution and joins a trivial solutions again. So in the next slide, this figure is mode 1 branch for several values of gamma 2. In this case, the vertical axis represents B1, and D1, D2, gamma 1 are fixed, and gamma 2 changes this value, and the largest branch is for gamma 2 equals 0.5, and gamma 2 becomes larger, then loops of branches becomes smaller in this way. Every branches emanate from trivial solution, but its goal are different. Gamma 2 is between these values. They joins mode 2 branch, but when gamma 2 is this value, then it joins not mode 2 but mode 3. And gamma 2 is this value, it joins trivial solution. This figure shows a note on mode 2 solution. In the left diagrams, mode 2 branch red curve emanates from trivial solution and joins a trivial solution again, and the wave profiles of the solutions at the point A and A prime are like this. But in the right figure, the wave profile of solutions at the point B and B dash are like this. Very different, because the mode 2 branch emanates from trivial solution and joins mode 4 branch. And these figures show there exist lots of bifurcation solutions densely. In the left figure shows diagrams of mode 1 and 2, and around them there are mode 1, 3 and mode 3 solutions around them very densely. So hence we had to compute carefully not to jump to another branch. Then finally, the case of gravity waves. The most part is the same as capillary gravity waves, except the condition for bifurcation. It is given by this equation. And there is a case that this equation has two positive solutions. And this is example. Gamma 1 and gamma 2 is this value. And in this case, bifurcation points 2, let's lambda 1 and lambda 2. And the mode 1 branch from lambda 1 and mode 1 branch from lambda 2. And on the branch from lambda 2, a stagnation point appear like this. But from on the branch from lambda 1, we cannot find stagnation point. But here, it seems figure B implies an appearance of stagnation point, but we couldn't compute anymore because we need large-scale computation. The second example, two the bifurcation points, and gamma 1 and gamma 2 is like this, opposite sign to the previous example. And in this case, stagnation point appears omega 2, where gamma 2 is positive. That the previous example, stagnation point appear in omega 1 where gamma 1 is positive. And in this case, stagnation point appears in positive gamma. And in this case, from on the branch from gamma 1, we cannot find stagnation point. In the case of gravity waves, a stagnation point appears in these three places, only three places. But in all of them, a stagnation point appears in the side of positive vorticity. It is much harder to compute gravity waves than capillary gravity waves because much more division number and some technical idea is required. So it is our future task. Now, let me summarize. Regarding stagnation points, for capillary gravity waves, we see more stagnation points as the traveling speed is slower. And where a stagnation point appear depends on the combination of depth and vorticity. Regarding bifurcation structure, for water flows consist of two layers with piecewise constant vorticities. Bifurcation structures of mode 1, 2 are quite different from those of irrotational flow and also different from one layer of constant vorticity. This work just started recently, so we would like to make more systematic computations in order to classify solutions. Finish. Thank you very much.
Thank you very much. little time for discussions. Maybe you want to comment on that?
Well, I have a question here. Maybe I got distracted, but or kindly remind me. When you have constant, you have the constant vorticity on one layer, constant vorticity on the other one, and then you have a method to find, if I understood right, which the interface f of x, right, which just separates the two constant vorticities, right? So, is that correct? And how is that? I maybe missed the setup. So you choose maybe the vorticity in the lower layer, you choose the vorticity in the upper layer, and then you have like a Newton sort of scenario to calculate the interface. Is that correct? And what's the conditions that leads you to this interface? I maybe missed it. I maybe got distracted. I don't know.
Considered formulation.
I mean, it's all this combinatorics, right? Plus 0, 0 plus, and so on.
Yeah.
Very, very interesting. But then how you start it up? How you choose the f of x?
Yeah, so your question is, okay, not this one? Or your question about the numerical?
I mean, how is the, let's see.
The interface is P1.
It's just another streamline.
Yeah.
Well, it's just a streamline,
Yeah.
right?
Yeah.
Okay.
So it is embedded into U, capital U.
Oh, okay, okay, sorry, yeah, okay, got it.
The streamline where the vorticity changes. But
You just choose a streamline, you basically, okay.
Oh, yes, please.
Very similar to the last question. You have the interface and the free surface as harmonic series. You have them as cousins. How many terms do you take in your series? You have a parameter m, which I think was
Parameter N?
m. M is a summation. It's on one of the transparencies.
Oh, 수치 technically. You mean the numerical parameter?
Numerically.
We divided horizontal variable into
Okay.
400,
So how many harmonics did you take?
16.
16.
before.
Yes.
Other questions? There's one more, yes, please.
I mean, this is for capillary gravity and for gravity. And capillary?
Capillary? No, we didn't consider.
Yes, it's just, I was just wondering. Okay. Because that could also be, I mean, it's the same setup, no? Or
Yeah.
Yeah. Just set G equals.
That's right, but we have not
Yeah, yeah,
considered.
okay. But you could easily, no?
Ma-
Possibly, yes.
Professor Toland?
Maybe some shearing, right?
You describe the vorticity distribution as being in two layers. Is there any difference between that and saying that there are two values for the vorticity, which could be in
Same
three
thing.
layers, top,
Same
the bottom, and the middle being different, or four layers? You say that you're dealing with vorticity with two values.
Yes.
But that's not the same as saying that there are two layers for different vorticity. There could be four layers of different vorticity. It could be sliced up, could it not? Is it not the vorticity distribution that matters rather than the layers?
Oh, that is your question. Yeah, right. Right. But in this formulation, we can't consider
Yes,
that.
in this formulation, you choose to have two layers. Yes.
That's right.
But is that obvious that that's the right thing to do?
Wow, that's a good question. But do you have better idea?
I have ideas, but
Really?
not better ones.
Okay. Let us know it. Then we will compute that.
I have one question. For internal waves, for example, when you have these cells, you have this rotating cores. What happens physically is that the particle velocity tries to overcome the wave speed. The local particle velocity tries to overcome the wave speed. So then you can have these cells. But then turbulence develops. So has this any relation to what you observe in these studies, that the particle velocity tries to overcome the wave speed and then you have this bifurcation? Does it happen, or is it it must be also other mechanism?
Yeah, good question. This formulation doesn't answer your question. Yeah, but
Because what
I think
happens
you're
then?
right.
What happens then if you continue the theory?
Yeah.
But in parallel, you do an experiment.
Yeah.
In the experiment, you get turbulence, and the theory, well, you don't get the turbulence. So it's
I think you are quite right, but again, I don't know.
please look at that. If there is not any more questions, we can have a coffee break. No more questions? Okay, thank you very much.